This will be the final presentation in the session here this morning.
Oh, great. Well, if you give a professor a chance to speak, they don't want to stop. So
yeah.
I'll fully utilize the next 1 hour.
Okay, there you go.
So wanted to thank NASA and TFAWS, for the opportunity to present this work over here. So primarily the applications we are looking at is thermal energy storage, and we looked at two different vehicles for achieving this objective. So we looked at nanofluids for sensible heat storage and phase change materials in heat exchangers for latent heat storage. And we looked at machine learning as a mode for predicting either the real-time performance of a thermal energy storage platform or for predicting the materials properties of nanofluids, particularly their specific heat capacity. And ultimately, this led to a student project by an undergraduate student team that used the 3D printing or advanced manufacturing for making heat exchangers that were subsequently deployed on a self-driving car, which is basically an electric car. So hang on, there are a lot of things to cover over here, and I'm glad that I got the one hour to talk about it. So in terms of the contents, the first part of my presentation will cover this thing called nanofin effect, where we found some very counterintuitive results when we were using nanoparticle additives to coolants or nanoparticle coatings on heaters, where we found that a nanoparticle with lower thermal conductivity gave higher vapor production, or for that matter, a nanoparticle with a lower heat capacity than the coolant fluid actually enhanced the heat capacity. So to answer these conundrums, we had to resort to a particular model that we call as the nanofin effect. So that will be the first part of my presentation. And then the next part of my presentation would be on phase change materials and their deployment in heat exchanger configurations, particularly 3D printed heat exchangers. And we are looking at machine learning both for the nanofluids as well as the PCMs. Now, both within my research group as well as outside my research group, some of the questions that we try to answer are, is this four-letter word nano justified in terms of thermal fluids research? And if one could justify application of nanotechnology, the next question is what type of nanoparticles should you be using, and where should you be using? Should you use it in the ice box of your refrigerator, or should you use it in the condenser, or do you put these nanoparticle additives in the refrigerant itself? What gives you the most bang for the buck? And then there is the manufacturing issue, which is which type of nanofabrication technique should you be using? And then there's a design question: how nano should you go? Does a 5 nanometer particle give you better performance than a 10 nanometer or a 100 nanometer particle? So these are the type of questions that we are that keeps us awake at midnight in our research group, and I'll be answering a few of these aspects in my presentation today, and then I'll finally end with the acknowledgements. So before I get started, I would like to acknowledge all the hard work done by my research group. This is our research group picture taken a few years ago. And since after leaving my job in Silicon Valley, joining Texas A&M in 2005, in the last 17, 18 years or so, we have been very fortunate to graduate 18 PhDs and 23 masters from our group. And I get to show you all the pretty pictures, but there's a lot of hard work and toil and creativity and sweat that goes behind all these results. And I'm really grateful to my students for some of the breakthroughs that we had in our research group was thanks to their hard work. And I get to do the easy job and show you pretty pictures here. So in terms of our research group, we have a little bit of schizophrenia. A part of our research group works on thermal management, and then the other part of our research group works on micro nanotechnologies. So in the last 17 years or so, we have been fortunate to do more than 60 projects. But today my presentation is probably going to focus more on the nanofluids and nanofins, and then in terms of these nanoparticle coatings for enhancing boiling and condensation, and then finally also phase change materials. So the outcome of this work has been a book, a distance learning course that's part of the ASME distance learning curriculum. And then also one of my former students decided to leverage these technologies and start a company that won a few prizes in a business pitch competition several years ago, and also led to a few patents. So a little bit of an executive summary of what I'm going to be showing you. The first part is, of course, on the nanofluids, where and the genesis of this work was when I was a summer faculty, ASME, summer faculty program. I was visiting Air Force Research Lab, and there we were looking at polyalpha olefin, which is typically used for as coolant for avionics components on the F-35 or the F-16, for example. Aircraft. So the idea there was, if you take this coolant called polyalpha olefin and add nanoparticles at very tiny concentrations, the expectation was it would enhance the overall thermal conductivity of the mixture. But to our surprise, we found that the heat capacity went up as well. But that was not supposed to happen, because polyalpha olefin typically has a heat capacity of 2 joules per gram Kelvin. Nanoparticles typically are about 1 joule per gram Kelvin or less. So if you mix 1 and 2 together, you don't expect the number to be 2.1 on an average basis. You would expect it to be somewhere between 1 and 2. So the first time we did it was with exfoliated graphite nanoparticles. The first summer I was visiting Air Force Research Lab, and the enhancement there was about 50%. The second summer I was there, we tried it with carbon nanotubes, and there the enhancement in viscosity was about 20%. And not only that, the enhancement in heat capacity was 20%. But not only that, polyalpha olefin, which is a Newtonian fluid, started behaving like a non-Newtonian fluid once you added nanoparticles to it. And the viscosity enhancement could be anywhere between 10% to all the way 10 times enhancement in viscosity, depending on the temperature range in which you operate. So at that time, we could not make sense of it, but we pitched this idea to DOE, Solar Energy Technology Program, for molten salts. And molten salts have very poor thermal properties, both in terms of thermal conductivity and heat capacity. And by that time, I had about 4 PhD students working on this project, and we were able to crack that nut. We figured what is responsible for this enhancement, and once we understood the beast, we could control it, and we could actually double the heat capacity of molten salts for solar thermal applications. Now, in parallel, while I was doing all this work at Air Force Research Lab, in my own lab here at Texas A&M, we were experimenting with nano coatings for enhancing boiling. And so the first time around we tried it, we put nano coatings on heater surfaces using carbon nanotubes. And the enhancement in the critical heat flux was about 60%, and the enhancement in film boiling was about 300%. And to date, our research group is the only one that has film boiling data for carbon nanotube coatings on heaters. So there was no surprise there. We expected the heat, the vapor production to go up, but we were actually barking up the wrong tree. So just to explain what I mean, on the top right corner, you see a CFD simulation of a bubble forming on a heater surface. And this is for a film boiling configuration, this particular CFD simulation. And so we did the momentum equation in the vapor and the liquid layer using a Lagrangian technique, where you do a regrading every time step as the vapor bubble changes shape. And then we also coupled it with the energy equation, involving the temperature drop in the heater. And what you notice is, once the bubble develops a neck, it immediately forms a cold spot right under the bubble, which is marked in blue. And the significance of this cold spot is that more than 60 to 70% of the total heat transfer that's occurring under the bubble is actually occurring in that blue region, what we call as the cold spot. And our computer model predicted that if you can enhance the thermal diffusivity of your heater surface, the cold spot will be wider, which makes sense. And so by that token, we said, okay, if you put nanotubes in there which have high thermal diffusivities, it should enhance the cold spot. That was the angle with which we were doing the experiments. And so, but we were not really sure how much of the enhancement was coming from the higher surface area caused by this nano coating. So we decided to do this experiment using silicon nanofins that were etched on a silicon wafer, and we repeated the same experiment. And silicon has a lower thermal conductivity and diffusivity than carbon. But to our horror, silicon actually gave us higher critical heat flux. And we consistently demonstrated this for flow boiling as well as for making nanocoatings on condensers as well as for spray cooling. So this is kind of like the executive overview, where we see a lower heat capacity nanoparticle giving you enhancement in heat capacity, and then a lower thermal conductivity nanoparticle actually giving you a higher vapor production. So how do you resolve this conundrum? So to explain this, we resorted to this model, what we call as the nanofin effect. So the way we envision the world, it's kind of like 5 blind people trying to figure out an elephant. And typically we are operating in a regime which is below the wavelength of 300 nanometers, which is below your visible wavelength. So we are actually operating like these 5 blind men trying to figure out an elephant. And so currently the elephant, the way it looks to us is basically, if you think about a nanofin sticking out of a surface, your solid, as demonstrated in the schematic on the right-hand side. Initially, we thought of this model as a resistance network, where you have a conduction resistance within the fin, and then you have a sort of a convection resistance in the fluid, which is your standard fin model that we teach in our heat transfer class in our undergraduate and graduate classes. But turns out when you are operating at a very small scale, where the size of your fin is the same as the intermolecular spacing, you get an additional resistance called a Kapitza resistance. And so turns out this Kapitza resistance is the interfacial thermal resistance that dominates the game at nanoscale. And typically for silicon, this Kapitza resistance is much lower than for carbon. So even though silicon has a higher fin resistance, the total resistance for silicon is actually lower. So once we had this sort of insight, we came up with this monograph, which is basically 70% of Navdeep Singh's PhD thesis. And then subsequently, we did a project with GE, where GE was interested in figuring out how much of erosion or corrosion is caused by these nanoparticles as they flow in a conduit. And again, we found that instead of higher erosion, the precipitated nanoparticles actually reduce corrosion by anywhere between 50 to 100%. And so this was a work we did in collaboration with a materials scientist, Dr. Diana Bierman, at University of North Texas, and we published this work a few years ago. So coming back to this, this whole idea of leveraging cold sparks, we decided to make nano thermocouples, or what we call as thin film thermocouples, to study these cold sparks, both in the presence of these carbon nanotube coatings as well as in the absence of these carbon nanotube coatings. And having these nano thermocouples actually gave us a lot more insight into these length scales and time scales, because we were able to couple it with molecular dynamic simulations as well as boiling chaos models. And I'll come to that in a minute. So here is a configuration that shows a nano thermocouple, consisting of we used a K-type thermocouple. It was a chromel and alumel. So you have one line which is chromel, and then the other line which is alumel. And wherever they join, these two triangular sort of configurations, wherever they join, that's where you get the nano thermocouple junction. That's exactly where we are measuring the temperature. And then right next to these nano thermocouples, we were able to put a nano coating of carbon nanotubes. And typically these were about 8 to 16 nanometers in diameter. I notice I have a printing mistake here on the slide. They were about 9 to 25 micrometers in height. And I apologize, it's showing up as millimeters, but it's actually a micrometer. So about somewhere between 10 and 25 microns in height. We actually worked with 2 different heights of carbon nanotube coatings initially, and they were pretty well vertically aligned. As you can see in the picture in the top left, picture that shows it like a toothbrush. It's more like a forest of carbon nanotubes. And so we put this in our boiling rig, and we did boiling experiments with PF5060, which is a refrigerant made by 3M. And so the top left picture is a carbon nanotube forest that I had shown earlier, integrated with nano thermocouples, so we could measure the the surface temperature of the heater. And then, we were also able to measure the wall heat flux by mounting it on a copper block that was heated with cartridge heaters. And so if you plot the boiling curve, which is your wall heat flux plotted as a function of wall superheat, the lines marked in red and filled black icons are the carbon nanotube coatings. So one is 10 micron, and the red marks are the ones that are coated with 25 micron carbon nanotubes. And there are a lot of nuances here, but in the interest of time, I'm just going to focus on the primary nuance here, which is the critical heat flux got enhanced by 60%. And so we went back, we took that same type of silicon wafer, we etched nanofins. These are about let's see, 200 nanometers in diameter on a 100 nanometer diameter on a 800 nanometer pitch, and we could grow them anywhere between 10 nanometers all the way to 700 nanometers in height. And again, there are a lot of nuances here, but I'll just focus on the critical heat flux. And silicon with a lower thermal conductivity gave a 120% enhancement in the CHF, which again did not make sense initially. So, if you think of this whole nanofin as a resistance network, if you do the numbers, the ones that dominate are the fin resistance and the Kapitza resistance, which is marked as RK. And if you do the numbers, the back of the envelope, estimates using a one-dimensional conduction model. If you look at a carbon nanotube, and I have normalized the numbers here, these are non-dimensional numbers, even though I'm calling it ohms, it's not really ohms, just for your visualization purposes. So if I think of this as a resistance network, the resistance within the carbon nanotube is about 500 ohms. The Kapitza resistance for carbon nanotube is about 1000 ohms. So you're getting a total resistance of about, let's say, 1500 ohms. On the other hand, if you look at the numbers for silicon, the fin resistance is 675, let's say about 700. The Kapitza resistance is only 1 ohm. And so your net resistance for silicon is actually half that for carbon. So it's not the fin resistance that dominates the game. It's the Kapitza resistance, the interfacial thermal resistance that dominates the game. And what we find is that the critical heat flux ratio is also about coming out to be a factor of 2 between the two cases. So based on this insight, we came up with a hypothesis. We said that glass, silicon dioxide, is actually going to perform better if you make a nanofin out of glass compared to carbon nanotube. And then nickel, which is a metal, according to our prediction, was supposed to give us the lowest total resistance. And so therefore we predicted that a nickel nanofin will give you the best boiling performance compared to carbon nanotube. And silica, which is very heretic, if you tell this to the materials community, they will probably get mad at you. But silica actually, silica nanofin performs better than a carbon nanotube nanofin, just because the Kapitza resistance is much lower for silica. So we pitched this idea to NSF. They took a risk on us, and thankfully, we got a grant to test out this hypothesis, and we did the experiments. And sure enough, carbon nanotube gave us the lowest CHF. Glass nanofins actually gave us better CHF enhancement than carbon nanotubes. And of course, nickel actually performed a lot better. And if you notice, this curve is not on a straight line. You're sort of seeing a saturation curve. And part of the reason, I think, is we are estimating the total resistance to be wrong. I wouldn't say wrong, but we are probably making a big error on the estimation of the total resistance using molecular dynamics simulations. Part of the reason is molecular dynamics simulations cannot account for the electron gas that occurs in metal crystal structures. And so that interaction between the electrons in a metal lattice with the coolant is something that we are not capturing right now. And so therefore, I think we are probably over predicting the resistance when it comes to nickel and carbon nanotubes. There is also another effect. We call it thermal diode or thermal rectification. So if you have a hot nanoparticle and a cold fluid, you induce a concentration gradient of the solvent molecules from the surface of the nanofin to the bulk. And so when you have a hot nanofluid, both your temperature gradient and the concentration gradient are in the same direction. On the other hand, if you have a hot liquid and a cold solid, now your temperature gradient and concentration gradient are actually fighting each other. And so if you do the math, if you calculate the Nusselt number based on the Sorey effect and the Dufour effect, and if you take a Nu sub F as the heat transfer in the forward direction, which is hot solid to a cold liquid, your temperature gradient and your concentration gradient are actually helping each other. On the other hand, if you have a Nusselt number backwards, then your Nusselt number backwards, they are actually competing with each other. So if you subtract the Nusselt number forward from the Nusselt number backward, you get a net term which is proportional to the concentration gradient. And so, in other words, you get for the same temperature drop, a hot nanoparticle actually pumps more heat than a cold nanoparticle, getting pumped with heat from a hot fluid, essentially. So that was a revolution, based on this work. And so this is what we call as the nanofin effect, where you not only have a resistance, but you also have a diode. But the surprise was we figured that there is a capacitance also. There is an interfacial capacitance, there is an interfacial resistance, and there is an interfacial diode as well that comes into the picture. And that also in turn, I don't have time to talk about the corrosion part today, which also results in reduction in corrosion essentially. So coming to the capacitance part, how do we figure out this capacitance that occurs on a nanofin? But before I get into that topic, I just wanted to let you know that we did experiments. We have a flow boiling rig where we did these experiments with carbon nanotube coatings for boiling of water and as well as refrigerants. We also looked at a compact condenser with microfins on a copper plate fin configuration. And we coated it with carbon nanotubes, and we got an enhancement in the net heat transfer coefficient. We were able to double the net heat transfer coefficient. Well, I'm telling you the rosy part. The consequence of this is it's very hard to build old Reynolds analogy. So when your heat transfer goes up, your pressure drop goes up, by a factor of 8 if you're enhancing your heat transfer by a factor of 2. So that's a wall that one has to climb. One other work I wanted to showcase is Scott Hansen, currently at NASA Johnson. This was his master's thesis when he worked at Air Force Research Lab as a summer trainee, when I was there as a summer faculty, where we looked at these nanocoatings for spray cooling. And what we found was that with nanocoatings, the spray cooling was actually enhanced by a factor of 5 to 7, depending on the operating regime. So in the interest of time, I'll skip those results. And then subsequently, we found that even a 100 nanometer bump on a surface can enhance boiling. So in one sense, these nanothermocouples, which are a 200 nanometer road bump on the surface, can actually enhance the boiling. So the act of measurement can enhance boiling. So we were on the lookout for a better, heat transfer and temperature measurement platform on the nanoscale. And we found this particular configuration that was used for measuring skin temperature for cancer patients using diode nanosensors. So it turns out the forward direction current as well as the backward direction current in a diode scales as the temperature. So if you hold a diode to a particular voltage and you measure the current as a function of temperature, you can actually use that diode as a temperature sensor. So now we have a temperature sensor that's about 5 to 10 nanometers below the surface that does not create a surface bump and is able to measure temperatures. And we proved this for spray cooling applications. Now these nanothermocouples, we could also use these nanothermocouples to look at the time temperature trace for different boiling regimes, like fully developed nucleate boiling, critical heat flux, as well as film boiling. And we saw that the chaos signature of these, these thermocouple plots, if you do it as a phase plot, the signatures of the chaos that comes out of these temperature plots actually changes depending on the boiling regime. Or in other words, if I have a nanothermocouple measuring temperature on a surface for a long time, just by looking at the type of fluctuation I'm getting, I can characterize the type of boiling regime that I can get on this heater surface. Now, coming back to this idea of nanofins as a thermal capacitor. So, this is a work that we did at Air Force Research Lab, where we had a flow loop where there is a hot oil loop with a fin, heat exchanger on one side, and then a cold water loop on the other side. And what we decided to do was the hot oil loop contained polyalpha olefin, and we put nanoparticles in the flow. And we looked at the characteristics of the material properties as well as the type of thermal response that you get. And so here is some raw data. So, on the top are the graphs that are plotted for heat flux as a function of flow rate. The red circles you see in the bottom are for pure polyalpha olefin. The blue dots are polyalpha olefin with 0.3% by mass graphite nanoparticles, exfoliated graphite nanoparticles. And then the green light dots are the heat transfer data for nanoparticles, exfoliated graphite nanoparticles at 0.6% mass fraction. So in other words, you are putting this pixie dust at less than 1% concentration, and that's enhancing your convective heat flux by 10%. But there was no surprise here because even a decade before we did this experiment, starting with DOE labs, people had shown similar characteristics where you put nanoparticles and the convective heat transfer goes up. So we didn't really say anything new by this study. But on closer examination of the surface of these fins, these micro fins or millimeter scale fins, we found that these exfoliated graphite nanoparticles, which look like these transparent glass pieces marked by the arrow on the bottom right, were sticking out like nanofins. So in other words, the nanoparticles were precipitating on the heat exchanger surface and giving you an additional surface area for heat exchange. So you have a millimeter scale fin, which is decorated with nanoscale fins on their surfaces. And so that could be thought of as one mechanism for increasing the convective heat flux. And we did it with the carbon nanotubes as well. And you can see these carbon nanotubes precipitated as a bundle and gave you a nanofin at the same time. And again, but there was no surprise there. The surprise was when we measured the heat capacity of these mixtures. And so the misunderstanding in the literature at that point was people would measure the thermal conductivity of the nanofluid, they would measure the convective heat flux increase in the nanofluid, and they would assume the mixture rule for the heat capacity of nanofluids without measuring it. But one of the big advantages of being at Air Force Research Lab was we had ready access to a heat capacity measurement platform with a technician. So we didn't even have to learn how to use it. The technician did the measurement for us. And what we found was the bottom triangles are the pure neat polyalpha olefin. And even at like 0.6% mass concentration of these exfoliated graphite nanoparticles, whose heat capacity is about 1 joule per gram Kelvin, the heat capacity increased by about 50%. And it did not make sense. And then we repeated it for carbon nanotubes. The profile of this graph was a little different, but still we got enhancement anywhere between 10 to 15%. 10% enhancement at higher temperatures, 50% enhancement at lower temperatures. So the question is, where is this enhancement coming from? So we resorted to molecular dynamics simulations, and I have to acknowledge my colleague here at Texas A&M, Dr. Jayan Reddy, who's very famous for computational modeling, and he helped us incorporate molecular dynamics in our research group, through his postdoc. And so the way this molecular dynamics works is you take a computational cell, you put in a nanofin here. The top left shows a carbon nanotube being put into the cell. And then you populate it with your molecules of the particular fluid that you want to study. And then you give sufficient kinetic energy to the nanofin that it goes up in temperature. And then you see how the temperature decays with time as these crystal lattice of this nanofin interacts with this vibrating molecule. And so this decay curve of change in temperature with time, which is shown in the bottom left and the bottom right, that's your rate of change of temperature with time, or what we call as the tau in this equation on the bottom. And that's proportional to the resistance as times the capacitance of your nanofin. And so by using this molecular dynamic simulation, we were able to predict the Kapitza resistance. But once we looked a little closer into this final equilibrium configuration of these molecules around the nanofin, what we notice is right around the nanofin, you form a cluster of molecules that have a higher density. And you sort of see this density oscillation wave that decays with distance away from the surface of the nanofin. Or in other words, when I'm putting a nanoparticle in water, even at room temperature, I'm going to get ice around the nanoparticle, only about 2 nanometers thick. And interestingly, that ice is not going to be natural ice. It's going to mimic the crystal properties or the crystal spacing of the nanofin on which it has formed. So, that will probably have a different property than the ice that forms on a snowy day. And you don't have to take my word for it, because a computational simulation can sometimes give you garbage. So here is a picture on the right that was, we reproduced it from Science, not our work, where they took a picture using a high resolution tunnel electron microscope, HRTEM. And sure enough, you can see that on the sapphire crystal, liquid aluminum layers up with a dense layer. And the interesting thing you notice is that liquid aluminum molecules right on the surface of the crystal are mimicking the crystal lattice, actually. So it's spacing up with the same spacing as the top layer of the crystal lattice. So that's experimental evidence of what we show numerically as well. And here is the experimental data where we put a molten salt, a carbonate eutectic with silica nanoparticles in there. And molten salt essentially is amorphous once it solidifies. And what you see is, these nanoparticles, which are these white dots, about somewhere between 20 and 60 nanometers in diameter. And right around the nanoparticle, you see a semi-crystalline layer of this amorphous salt that formed after solidification. And later on, we showed that if you dissolve this, actually one of my former students did these experiments once he became an assistant professor, and he showed that if you dissolve these semi-crystalline layer away from the nanoparticles, the enhancement in heat capacity goes away. So on the left, you see the bottom line, blue and orange, is pure molten salt. And the moment we add 1% by mass of silica nanoparticles, which are about 50 nanometers in diameter, nominally they're between 20 and 60 essentially, the heat capacity goes up by 26%. And we think that it's because of this compressed layer that forms around the nanoparticle. So in the interest of time, let me switch. So in other words, if you use the simple mixture rule, this is actually wrong, because this does not account for the compressed layer that forms around the nanoparticle. So the correct equation to use is if I'm using 1% by mass of nanoparticles, which is your x here, times the Cp of the nanoparticle, then you can calculate the mass fraction of this compressed layer that forms around the nanoparticle. Let's say if it is a 2 nanometer thickness layer of compressed phase, you can estimate what this y will be, and you multiply it by the heat capacity of the compressed phase, which is typically the solid phase heat capacity of the fluid, or the solid state heat capacity of the fluid molecules, and then the remaining mass fraction times the heat capacity of the fluid. So once we use this equation, it matches the experimental data very well. And what we realize is that this compressed layer that forms around the nanoparticle is the capacitor. That's the one that is storing heat, and that's what is giving you the heat transfer, the heat capacity enhancement. Now, we had an accidental discovery where we found that you don't need to add nanoparticles. If you add surfactants and heat it, the surfactants carbonize and give you carbon onions. And we found that as you keep increasing the surface, the concentration of the surfactants, the heat capacity keeps increasing until it hits an optimum, and then the nanoparticles start agglomerating and there is a decrease in the heat capacity. So again, that's a very accidental discovery. You don't need to buy $100 a kilogram nanoparticle. You just buy $1 a kilogram or 50 cents a kilogram soap. You mix it up, you heat it in a microwave, you are drinking carbon onion, not nano onions essentially. So we also have a molten salt nanofluids flow loop where we did some testing for under flow conditions. In the interest of time, I'll skip it because the focus of this work is on machine learning. So as you can imagine, there are so many variables that can affect the properties of a nanofluid, and the interactions between these different transport mechanisms is unknown at this point. How they couple up non-linearly. There are very few physics models out there to capture that rich variety of those interactions. So in an environment where all the interactions are unknown, machine learning is your friend. So we did some preliminary study to predict the heat capacity of molten salt nanofluids, primarily nitrate salts or solar salts that are typically used in solar thermal applications. And the picture on the right shows a typical artificial neural network, a multi-layer perceptron model that we used in our in our prediction models. And without getting into too much details, I can answer the details of the computational procedures. We did the prediction for the heat capacity of different nanofluids as a function of temperature by training the model using existing data that we have in our lab. And we found very good, prediction capabilities, both for training as well as validation, as well as for, testing. And so here, this one shows the different errors that we got using, a whole bunch of different types of NN models. We tested out different types of optimization procedures. And what we found was, depending on how you do the training, you can end up with different levels of error. But the take-home message is, using this technique, we were able to do predictions with errors with less than 0.1%, in the prediction of the heat capacity properties of these molten salt nanofluids. So now I'm going to change gears here. I'm going to talk a little bit about phase change materials. Instead of sensible heat as your thermal energy storage vehicle, how about looking at latent heat? And before I go there, I'm sorry. So in summary, for the nanofluids, interfacial thermal resistance dominates the conduction thermal resistance, the total resistance essentially. The compressed layer that forms around the nanoparticles or nanofins is like a thermal capacitor that leads to thermal storage, and a consequence of this interaction of these fluid molecules with a solid surface results in the formation of a diode, a thermal diode, where a hot nanoparticle actually gives you more heat transfer. But the most fundamental insight we got from this study was it's not the nanoparticle, it's actually the fluid. Or in other words, the solid phase of the fluid molecules is what is dominating the game. So if I have a choice of nanoparticles and if I have a choice of coolants, the primary variable I'm going to be focusing on is the coolant, not the nanoparticle. And I'm going to select the coolant that has the best properties in the solid phase. The nanoparticle is there just to serve as a surface area amplifier so that the ice phase can form around it. And also to some extent, the surface energy of the nanoparticle controls how thick that ice layer will be. Will it be 2 layers or 2 nanometers or 5 nanometers? So to some extent, nanoparticles play a secondary role. The primary role is actually the solid phase of the coolant. Now let me, so the other breakthrough we had was you don't need to add nanoparticles, add soap and heat it up. And this is critical for industrial applications, particularly if you're trying to do industrial scale up. So if you think of a concentrated solar power, thermal energy storage tank, which is, let's say, a 30,000 ton tank of, molten salt, even if you're adding 1 ton of nanoparticle and trying to mix it, it's a pretty uphill battle. On the other hand, it's much easier to mix it with surfactant and soap and heat it up, and hopefully that soap generates the nanoparticles for you. And that's a much more tractable proposition from an industrial scale application point of view. And so we were able to come up with a simple analytical model as well as a machine learning model for predicting the heat capacity. And we also looked at, the performance of the nanofluid, for viscosity enhancement. But, I'm skipping that part for my presentation today. So let me change gears. Now let's look at thermal energy storage using phase change materials. And we were looking at it from a water energy, food water energy, nexus, or food energy water nexus applications, particularly for sustainability, reliability, and resilience, type of perspective. So very briefly, this is what I'm going to be presenting. So there is a lot of interest in using phase change materials for dry cooling of power plants. But the enigma there is, typically salt hydrates are considered as an attractive material, but salt hydrates actually have very poor reliability. In other words, it's very easy to melt them, but it's very difficult to, solidify them. You need a substantial amount of subcooling in order to initiate, solidification. And so we looked at the machine learning algorithms as a way to predict when you are going to hit a particular melt fraction. And so that's basically, and we wanted to do this prediction in real time. Let's say in a power plant, scenario where you are looking at the time temperature trace of temperature within a molten salt vat, and or of a phase change material vat, and you want to predict how much time you have before you hit 80% or 90% melt, because that's the point at which you want to stop. Because once you hit 100% melt, then it becomes an uphill battle to solidify that whole thing back. So just by looking at time temperature trace, both within the PCM as well as on the surface of the container, we were able to predict when a particular melt fraction would be achieved in a heat exchanger filled with phase change materials. That's basically the overview of this work. Now, the motivation of this work was actually for reducing water usage in power plants, or to make power plants that don't use a cooling tower. And so the primary application was, to reduce the strain on freshwater resources. The reason being, thermal power plants actually consume more fresh water than any of the other segments combined, including irrigation and public supply. So, so how do you make a power plant, independent of water? Well, your traditional wet-cooled power plants, they consume a lot of fresh water, primarily because of the cooling towers. But this is impossible to implement in a dry region. So in dry regions, people use dry-cooled power plants, air-cooled power plants. But you have bigger heat exchangers, they require a more capital cost. Their operating costs are also much higher, and their performance is pretty bad, in terms of the net overall heat transfer coefficient. But the main drawback is they're unreliable, particularly if you're operating a dry-cooled power plant in the Nevada desert, for example. On certain days of the year, the ambient temperature is higher than the turbine steam exhaust temperature. And so you have to shut down the power plant. That can lead to grid instability. So we were fortunate enough to be funded by the ARID program from ARPA-E. And the idea there was to use dry-cooled power plants. I'll skip this graph. So the idea there was to use phase change materials for cooling either the steam directly, which is a configuration shown on the left, by melting PCM instead of using the ambient air. The other configuration is to cool down the ambient air by passing it through a bank of PCMs. While the PCM melts, it generates the cold air that then cools down the steam. And then the idea was you flow the cold air at night, the desert air, and you freeze the PCM back during the night, and you melt it during the day. But the enigma there is you don't want to melt the PCM 100%, because if you melt it, now it requires a substantial amount of subcooling in order for onset of nucleation to work, and you have wasted precious hours at night just waiting for the PCM to solidify, or to initiate the solidification. So the way to get around it is to use what is known as the cold finger technique, which is you keep a part of the PCM unmelted. And so the graph on the left shows the amount of subcooling you need to solidify a PCM after a certain number of cycles of melting and solidification, where you have done 100% melting and 100% solidification. The graph on the right shows the amount of the subcooling that you need after like 800 cycles. If you don't melt the PCM completely, if you just keep about 5% or 10% unmelted, the onset of nucleation requires less than 1 degree subcooling in order to initiate the solidification process. But the enigma there is, how do you predict in an actual power plant when it's going to hit 90% melt? And that's when you want to stop and shut down that thermal storage platform. So with that idea in mind, we did, I'll skip this slide. So with that idea in mind, we came up with this machine learning configuration, artificial neural network configuration, where we had 3 inputs. Either they were the 3 thermocouples placed within the PCM at different heights, corresponding to different melt fraction, let's say 30, 60, and 80% melt fraction. We also looked at a configuration where we had 3 thermocouples mounted on the surface of the container containing the PCM. And instead of measuring the PCM temperature, it was just measuring the surface temperature. So it's kind of somebody putting their ear onto a wall and eavesdropping on their neighbor. In essence, you are not measuring the temperature of the PCM itself, you're just measuring the temperature response of the container at different heights. And from that, you're trying to back calculate and say how much of a melt fraction you have at a particular time. And then you are trying to predict how much time you have before you hit, let's say, a 80% or a 90% melt fraction. So we used PureTemp 29, which is an organic PCM. We used a fixed topology artificial neural network configuration just to prove the feasibility of this concept, and also to compare the performance of your machine learning algorithm when you are eavesdropping by measuring the surface temperature compared to the actual temperature of the PCM. So this was our experimental apparatus, the picture on the left, the schematic on the right, where we mounted thermocouples at different heights within this measuring cylinder. We put a nichrome coil at the bottom of the cylinder to melt the PCM from the bottom. And we measured this temperature time trace of these thermocouples for 3 different power inputs to the nichrome coil at 2 volts, 2.6 volts, 2.3 volts, 1 watt, 1.4 watts, and 1.6 watts essentially. So the graph on the top is the temperature time trace by the 3 different thermocouples placed at 30, 60, 85, and then we also put a 4th one at the 90% melt to compare the prediction versus what we measure in reality. The one in the bottom shows the surface temperature trace as well as the ambient temperature. And then the picture on the right shows the IR camera image of these molten melted PCM as it progresses towards the top of the measuring cylinder. And then we also had a camera recording the location of the meniscus every 5 seconds. So having all these data, we were able to come up with a label. So if Tm is the time remaining to reach a particular melt fraction M, so let's say I want to predict when it hits 50% melt fraction or when it predicts 90% melt fractions. So the label for my machine learning was the time remaining to reach a particular melt fraction. And so we used this particular configuration of our artificial neural network topology. We had 3 inputs, the 3 temperatures measured by the thermocouples, either on the surface or within the melt, or within the PCM at 30%, 60%, and 90% melt fraction locations. And we did the training with the experimental data. We set aside another set of experimental data for the validation and checking the error in our prediction. So we had 2 sets of prediction, one for the surface temperature, based on the surface temperature, and then one based on the PCM temperature. And let's see. So these were the uncertainty in our measurement in the experimental data. And here is the prediction, versus what we observed in the experiments. So what you see in the graph on the left is we took the 2.6 volt experimental data. We trained the ANN model with that data for 30, 60, and 85% melt fraction, thermocouples, and we predicted it for the 2.8 volt, experiment. And so on the x-axis, we have plotted the non-dimensional value of the time taken to reach 90% melt. This is the actual experimental data. The one on the y-axis is our prediction, and we see that initially the error in the prediction is pretty low, and then as we get closer and closer to the actual melt fraction, the error keeps increasing. And so this is based on the actual data from this is based on the data for thermocouples that are placed within the PCM, and we see that in the last 30 minutes. Our prediction accuracy is about 10 minutes, 10 to 11 minutes for predicting the time remaining to reach, let's say, 90% melt. Now, we did the same with using the surface temperature data, where we use, let's say, the 2.6 volt experiment for surface temperature for training the algorithm, and then we predict it for, let's say, the 2.7 volt or the 2.8 volt. And what we find is the error is a little higher when we are measuring, when we are training the ANN model using surface temperature data. On the other hand, the surface temperature data tends to do under prediction, which avoids catastrophic failure. So in other words, the surface temperature measurements are actually giving you less accuracy, but are more reliable. On the other hand, the ones that are based on the PCM, actual PCM temperatures are more accurate, but tend to be more unreliable because they tend to over-predict at times, and that can actually lead to catastrophic failure of your thermal power plant. So just to summarize, so the surface temperature-based training are more reliable, and then the PCM temperature-based training gives you less error. And so as a summary, as a conclusion, we get low errors as long as we are predicting within the manifold of our measurements. In other words, if my measurements are for 30, 60, and 85, and I'm trying to do the prediction for 90%, which is outside the measurement envelope, my error is higher. On the other hand, if my prediction is within the measurement envelope, I tend to get lower errors in my prediction, specifically if I'm using the PCM temperature data. Also, if the training data for power input and the prediction data for power input, if the two power inputs are close to each other, we tend to have less error. But if the power input for training is substantially different from the power input for the prediction, then we tend to have higher errors in the predictions. And then finally, during the initial stages of the melt cycle, when the melt fraction is less than 60%, the ANN model tends to typically have lower errors, and this is particularly true for ANN trained on PCM temperatures than for ANN trained on surface temperatures. And we get a lower error magnitude, for the surface temperature trained data in our measurements, essentially. We also found that if your thermocouple is uncalibrated, or if your calibration of your thermocouple goes off whack, you still tend to get pretty accurate data. And this is, I think, one of the biggest advantages of using a machine learning prediction engine. If you are going to use a corresponding CFD model, inaccuracies in your temperature measurement can actually end up with catastrophic failure in your predictions. On the other hand, because machine learnings are based on behavioral models, they don't care as much about the actual temperature value rather than the trend in the temperature time trace. And so a K-type uncalibrated thermocouple, we did those measurements and compared it against a calibrated data, also gave us pretty good errors or pretty low errors in our predictions. So in summary, we have proved the feasibility of artificial neural networks for forecasting CFD. We show that it improves the efficacy and reliability of incorporating the cold finger technique in an actual power plant. And so the target applications could be supplemental cooling platforms for leveraging thermal energy storage using PCM, particularly for zero water usage power plant. And particularly when it comes to electronic chip cooling, where people are Intel, I think, has a few patents now where they show where they're putting PCMs in the package of electronic chips for enhancing the transient thermal management of these chips, particularly gaming chips, for example. So what we show is you don't need to put the thermocouple inside the package. If you put a thermocouple on surface of your chip package, it can as well predict how much melt fraction you have at a particular time and how much time you have remaining before it hits a particular melt fraction. And so compared to having a thermocouple that's inside the package, if it goes bad, the manufacturing cost is higher, the repair cost is higher. On the other hand, it's much easier to put a thermocouple on your computer chip package. So even if the thermocouple goes bad, it's much easier to replace it. Or even if the thermocouple goes off whack in terms of the calibration, you are still able to use it. So your manufacturing cost is low and your maintenance cost is also low for a chip package that uses a surface mounted thermocouple and uses a machine learning engine to do the predictions. So The student worker who was actually working, an undergraduate student who was working on this ARID project, was also participating in the SAE, self-driving car competition. And so he came up with a brilliant idea and said, what if we make 3D printed heat exchangers and put PCMs in them? So these were some of the early models of 3D printed heat exchangers, a shell and tube on the left, a chevron plate heat exchanger on the right that the student tried initially. Subsequently, we also tried a few other configurations in terms of 3D printed shell and tube heat exchangers. And ultimately, we came up with this plate heat exchanger configuration that was 3D printed. And initially, we did experiments with ice in these heat exchangers. And subsequently, we did with 3 different salt hydrates. And this particular heat exchanger was put in a electric car that was reconfigured as a self-driving car. And the students, put this heat exchanger in the dicky of the car, and they used it to cool the electronic chip that does the machine learning algorithm for doing the visualization as the autonomous vehicle was, negotiating a track in the desert in Nevada. And they were able to successfully show that a 3D printed heat exchanger with salt hydrate PCMs in them could be used for electronic chip cooling. That chip was used for driving as the brains of the electronic of the self-driving car. And this particular student team won a whole bunch of prizes in that competition in 2017. So with that, let me stop here. So would like to acknowledge my students who did all the hard work, came up with the creative ideas. I only get to show you the nice pictures. In addition to our lab, we collaborate with a whole bunch of other facilities on campus, as well as at other universities. And again, this is the group a few years ago. So Navdeep Singh in the bottom is the guy who came up with the molecular dynamics models. Dong Shin, who's at University of Central Michigan. Navdeep is at University of Houston. Dong Shin is the one who made those breakthroughs in terms of the molten salt nanofluids, particularly where we have the soap nanoparticles, soap generating nanoparticles in situ. So these are the different members in the lab. Also would like to acknowledge all the sponsors in the last 17 years that have made this work possible. We did a whole bunch of SBIR, STTRs, both phase 1 and phase 2s from DOD and NSF and a couple of other organizations. And then, of course, the federal agencies are also listed here. And would like to acknowledge my collaborators at NASA, or formerly at NASA, at Air Force Research Lab, Navy, and DOE, as well as at other universities. And then I would like to acknowledge DARPA Micro Nanofluidics Fundamentals Focus Center that funded the molecular dynamics work that we struggled with initially and now is an integral part of our lab right now. And I'm also part of this new experiment at Texas A&M called Engineering Medicine, which is a collaboration between the College of Engineering and College of Medicine at Texas A&M and the Houston Methodist Hospital, where we recruit engineers and give them MDs after 4 years, and they also get a Master of Engineering. And these are my collaborators at the Houston Methodist Hospital as a part of the Burroughs Wellcome Fund. We have set up a new entity called Academy of Physician Scientists. So with that, let me stop here. My contact information is provided over here, and I'll be happy to take any questions.
Okay, thank you, Dr. Banerjee. Lots of good stuff going on there. Yeah, for the audience, we do have about 10 minutes here for questions before the lunch break. So encourage everyone to type your questions in the chat. Make sure you're sending it to everyone so that we see those questions. And there are a few questions here to start off with, so I'll go ahead and read them. Let's see here. Is there a lot of hydrogen bonding in water at the CNT interface?
Yeah, this is actually a very loaded question because there are a number of interactions that are going on at this scale, and I'm glad that you asked this question. I wish I had the schematic to show it, but I'll answer it verbally. So yeah, definitely, if you have a hydroxyl ion, particularly if you are doing it with water, and you can never get water that's 100% purity. Even at 0.0001%, you will have some impurity. And water being a polar fluid, you will get your hydrogen ions and the hydroxyl ions. And of course, your carbon nanotube, depending on how the carbon nanotube is manufactured or fabricated, can have an affinity for either hydrogen or hydroxyl ion, depending on whether you have surface oxidized the carbon nanotubes or not. And so in other words, depending on the configuration on the surface of the carbon nanotube, you can have a higher concentration of hydrogen ions on the surface of the carbon nanotube compared to in the bulk. So in other words, you have created a concentration gradient going from the surface of the carbon nanotube to the bulk. And similarly, if there are other ions, so let's say if you have put some sodium chloride as an impurity in the water, the carbon nanotube might like the sodium ions more than the chloride ions. And so therefore, you would also set up a concentration gradient for the sodium ions going from the surface of the carbon nanotube to the bulk. So in addition to these hydrogen bonding type of interactions, you can also have ionic interactions depending on the level of purity and the type of impurities you have in your coolant, whether it's water or any other ionic fluid. On the other hand, if you're looking at non-polar fluids like a refrigerant or like a polyalpha olefin oil, these don't typically tend to have ions in them, but there the interaction can be a little different if you have surfactants in your system, because surfactants tend to precipitate on nanotube surfaces, and that can lead to additional hydrogen bonding mechanisms there. So that interaction is very complex, but from a bird's eye view point of view, what you are doing is you are setting up these concentration gradients based on the type of interactions, molecular scale interactions you have between the nanoparticles and the coolant. So I didn't get to show that work. So in other words, polyalpha olefin comes in different flavors. You can have a straight chain polyalpha olefin versus a branch chain polyalpha olefin. And the interfacial thermal resistance for a straight chain polyalpha olefin will be very different compared to a branch chain. We actually showed this numerically in one of my students' work. And in other words, the same coolant, depending on the chemical structure of the coolant, will give you different rates of heat transfer, which is very heretic to how we teach heat transfer in our undergraduate classes. When we take polyalpha olefin, we don't really care about what kind of mixture that polyalpha olefin is. It can be 50% straight chain, 50% branch chain, or 80% straight chain, 20% branch chain. Depending on how that blend looks like, for a nanofin, you will get different types of heat transfer, depending on the blend of olefin oil that you are using in your coolant. And so that's very counterintuitive compared to the way we design heat exchangers.
Okay, thank you for that. And then there was a second part to that question too. Are there electrolytes in the water in the simulations or experiments?
So we did not, simulate for water. I'll confess, we simulated it for molten salts and polyalpha olefin, and I consciously stayed out of water. And part of the reason is, I'm a heat exchanger guy, I'm a boiling condensation guy, I'm not a chemist. And water is a very strange molecules. There are probably 80 different models of water if you look in the molecular dynamics literature. And I was totally confused. I didn't know which model would be appropriate for our system. And I didn't want to get into a garbage in, garbage out situation. So I didn't want to dabble in something that I don't understand. So I consciously stayed out of water because I have no idea which particular model of water to use, given our configuration here. On the other hand, molten salts, are less controversial in the molecular dynamics literature. So we decided to do this for molten salts and organic molecules like, alcohol, acetone, polyalpha olefin, hydrocarbons, and so on, because those are much more tractable in a MD simulation architecture. So that's where we did these predictions and measurements. And so we can sort of project what we get from the molten salt data to water, because we know no matter which model of water we use, even at trace impurity levels, you are going to end up with some ions in your system. And so you are guaranteed to get some amount of electrolytes as impurities in the water. So you are going to set up concentration gradients, which is going to set up that thermal diode. That's all I can predict. But I have consciously stayed away from these electrolytes in water just because I don't know the chemistry of it very well.
Okay. Thank you for that. And then there's questions from two more people. The next one here, at the end, there's a comment. Thanks for the thorough presentation. And then a two-part question. Are these models working the same in microgravity? And are the performance gains expected to increase or decrease on orbit?
Yep, that's a loaded question. I'm actually a member of the decadal survey for biological and physical systems, and these are some of the questions we are actually debating in the decadal survey this year. Frankly, I don't know. We have not tested it under microgravity conditions. Would love to test it under microgravity conditions. All I can, conjecture is I definitely expect that ice layer to form, because what we have found is this ice layer is fairly resilient to temperature. No matter what temperature you are at, they tend to be pretty constant in thickness. So I would assume that they are probably going to be pretty resilient as far as microgravity is concerned. But one benefit I see to microgravity is, nanofluid literature is replete with a lot of bad experiments where the nanoparticles were not stable in the solvent, and therefore they settled out and agglomerated over time, and people ended up with very controversial data. Particularly, you can trace it back to the stability of the nanoparticles in the coolant, and specifically because of gravity. So I would expect the nanofluids to work a lot better if you're looking at it as a coolant fluid or as a thermal storage, energy storage fluid. I would expect it to work a lot better in a microgravity condition compared to in Earth normal, or let's say moon gravity, or Mars gravity condition. So that's just a guess at this point.
Mm-hmm.
But so these, I think these models would work under the microgravity, because these models, we did not assume gravity in the models. So, so this is gravity independent prediction, actually.
Okay. All right. And then the last question here, this person also says, thanks for the presentation. The question, how does the fluids affect the stability of nanofluids, effect of size of nanoparticles?
Yes, I did not have time to get into this discussion, actually. Fluids, and that's also one of the fundamental insights we got from 15 years of doing nanofluids research. Fluids actually are a very important parameter in figuring out if your nanoparticle is going to be stable or not. So, for example, if it's a polar fluid like water or molten salts, you are trapping charges on the surface of the nanoparticles. So when two nanoparticles are approaching each other, they don't see each other. You can think of it this way. If you have charged a lot of if you have trapped a lot of hydrogen ions on the surface of the nanoparticle, this nanoparticle is now net positive compared to the bulk fluid. So when two nanoparticles are approaching each other, in addition to the van der Waals interaction, they are also sensing that there is a repulsion from a positively charged particle as they come closer together. And so that guarantees their stability, because that prevents them from touching each other and agglomerating. And so the pH of the fluid plays a big role. There is optimum pH at which you trap the highest amount of positive charge on the nanoparticle, let's say. So controlling the pH is very important when you are looking at a aqueous or a polar solvent for stabilizing the nanoparticles. On the other hand, if you come to non-polar like polyalpha olefin, there the strategy is to functionalize the surface of your nanoparticles so they get into better hydrogen bonding. I didn't get time to talk into that, and this is one of the reasons I'm so grateful to Air Force Research Lab. Because when we were doing the experiments, I got hold of people in the materials directorate, and they helped me to surface functionalize the carbon nanotubes with amine groups, and I'm trying to remember. There were a couple of surface functionalization strategies we took, but they advised me to do that, and that was a very good advice, because carbon nanotubes typically don't want to get into hydrogen bonding. But on the other hand, if you surface functionalize the carbon nanotubes, that enables hydrogen bonding, either with amine group or a carboxylic group, You boil the carbon nanotube in a carboxylic acid or a amine, functionalized acid, for example. You would get surface functionalized with these moieties. And that enables you to get a much better hydrogen bonding with the fluid, and that actually enhances the stability of the nanoparticles in the fluid. So making nanofluids is not as simple as I put some pixie dust and it gives you fantastic properties. A good amount of rigor needs to go into making sure that they are stable, because if they're not stable, they're going to agglomerate and precipitate out, and there goes the enhancement essentially. So and so the fundamental problem there is small variations in the synthesis protocol can give you very different material properties. So the same ingredients, depending on the order in which you cook, is going to give you different flavors. So one has to pay a very close attention to the synthesis and almost have military discipline in making sure that every batch that you make, there was no variation in the synthesis protocol. Because one of the things we found was even simple changes in the synthesis protocol, you can end up with nanofluids with vastly different properties. So the stability of the nanofluids is very important. Now, coming to the size of the nanoparticles, there is this other conundrum from a heat transfer design point of view. So the smaller you make the nanoparticles, the more ice layer you get as a per unit mass of the nanoparticles, because you have more surface area. On the other hand, the more surface area you have, more Kapitza resistance you have. So that's a trade-off. So if I'm designing a coolant and my objective is to maximize the thermal conductivity of the mixture, then the sweet spot is somewhere between 50 and 100 nanometers. This was actually predicted by Pat Phelan's group at Arizona State, and that model works beautifully. That shows how the Kapitza resistance changes and how that affects the net thermal conductivity of the nanofluid. On the other hand, if you want to maximize the heat capacity of the fluid for a thermal energy storage application, there the sweet spot is somewhere around 6 nanometers. It comes from this pipe d cubed by 6. That number 6 comes, if you feed it into that model, and if you assume it's a spherical nanoparticle, it automatically comes out from that, that analytical model that the sweet spot is somewhere around 6 nanometers. So in other words, if I want to enhance my heat capacity, then the optimum is 6 nanometers. On the other hand, if I'm trying to optimize the thermal conductivity, then the sweet spot is somewhere around 60 nanometers. And so the effect of the size of the nanoparticles on the properties, is a very, how do I say, is a rich topic for discussion. And I have not even touched on the viscosity, because one of the things that happens is these nanoparticles tend to form a percolation network. I can probably show a quick picture to illustrate what I mean. And I didn't get time to talk about it. So, and this also has a big implications for magnetic nanoparticles, actually. So what you see in this picture here on the right is every time a nanoparticle forms, you form that ice layer, the compressed layer around it. But that's like the first order interaction. The second order interaction is two nanoparticles seem to know that they are close to each other because they form a tentacle and they join with each other. And you end up forming a percolation network. And that tentacle forms, I guess, is because of the concentration gradient that you form between the two nanoparticles. And so in other words, this percolation network actually enhances the viscosity. And depending on how this percolation network forms, you can end up with a shear thinning or a shear thickening, nanofluid. And then on top of it, if you impose a magnetic field on top of this, you can think how complicated the scenario becomes, right? Particularly if it's a magnetic nanoparticle or the ice layer is, ferromagnetic, paramagnetic, depending on the type of magnetic interactions you can have. So there is a very rich, fundamental area this percolation network creates, that one could look into from a basic, science investigation point of view. But to a large extent, that percolation network depends on the size and shape of the nanoparticles, as well as how homogeneously distributed they are. So there are multiple parameters, and each of these parameters are nonlinearly coupled. So I don't think we understand all the physics yet very well.